Let's look at the epsilon delta proof of the product law of limits. Given that the limit of fx as x is approaching x naught is a, and the limit of gx as x is approaching x naught is b, prove that the limit of fx times gx as x approaches x naught is a times b. Before we move on to the epsilon delta proof of this real analysis problem, let's first revise on the epsilon delta definition of a limit. So what exactly is a limit? Well, given that we know if the limit of hx as x approaches x naught is L, then for all epsilon greater than 0, there exists delta greater than 0, such that if the distance between x and x naught is less than delta, then the distance between hx and L is less than epsilon. So this is the epsilon delta definition of a limit. And what it means is that we can get infinitely close to this value here as long as x, our independent variable, is close enough to this number we're trying to approach. Okay, so then moving back onto the problem, what can we get by using this definition? Well, firstly, we know that this is true, and this is also true. So then we know by definition, so this is our proof, by definition, for all epsilon greater than 0, there exists delta 1 greater than 0, such that if x minus x naught is the absolute value is less than delta 1, then fx minus a is less than epsilon. And similarly, for all epsilon greater than 0, there exists a different delta, delta 2 greater than 0, such that if x minus x0 is less than delta 2, then gx minus b is less than epsilon. So why do we have delta 1 here and then delta 2 here? Because delta 1 and delta 2 can be completely different things. And this is what we're trying to find in problems. We're trying to find the delta 1 and the delta 2 and like some other, maybe some delta 3 or something like that, that makes this statement work out as well. Because fx and gx can be completely different functions. So then clearly their delta 1 and delta 2 can be different, because for all epsilon greater than 0, there only has to exist one of these delta things. It's not like all of the deltas, all of the numbers greater than 0 have to satisfy this condition here. It's only one. And this one specific delta for every function and their limit can be different. Okay then, what do we want to prove? So we're not going to write this like on our answer sheet in the exam, but what do we want to prove? We want to prove that for some other delta, say delta 3, if the distance between x and x naught is less than delta 3, then fx times gx minus ab, that distance is less than epsilon. So that's what we want to prove. So now continuing our writing, right? What can we do? Well, we know that if, so this is like definition again, if this is true, this limit thing here is true, I'm not going to read it out, then for all epsilon greater than 0, there exists this new delta greater than 0, which is different from these two, or it can be the same, but we can't just assume they're the same, so we'll use a different symbol, such that if x minus x naught is absolute value is less than delta, then we have that fx times gx minus ab absolute value is less than epsilon. And we want to prove this is true. So you gotta do something with this side, the left-hand side of the expression, of the inequality. So what can we do? Well, we want to incorporate these into this to prove the delta thing, to prove the epsilon thing is true, right? And what can we do? Well, we can try to factorize this by adding and subtracting the same term here, i.e., this expression is equal to fx times gx minus, say we want to have this in part of our factorization, we want to factorize gx, right? We have a times gx plus a times gx minus ab. So we have this, right? And given that, we can then factorize this out. So we have gx, the absolute value of gx times fx minus a plus a times gx minus b, which perfectly also fits with this part, and we can use this also. So now we have what we want, or kind of like, at least we're not stuck in the same phase. What we can do now is, how do we make sure this is less than epsilon, right? Well, one way to do this is by using the triangle inequality, which is a really common method used, and it's like one of the most important inequalities. It's probably more important than all the other inequalities. It's like the most basic one here in proofs. So, according to the triangle inequality, if we have two variables, say, I don't know, bro, I and j, then, so three sides of a triangle, right? The sum of the two sides is always greater or equal to, or like greater than the third side, but let's just say greater or equal to. So we have that the absolute value of I, because it's a distance, plus the absolute value of j is greater or equal to the absolute value of I plus j. So the absolute value of I plus the absolute value of j. So that's like what we call the triangle inequality. And here then, if this is I and this is j, we can rewrite this whole thing. And this would be less than or equal to gx times fx minus a absolute value plus the absolute value of a times gx minus b. Okay, so now we have two separate absolute value expressions, and we have to make sure this is less than epsilon. So how do we do this then? Well, the most common thought process here is we want to prove that this is less than epsilon over 2, this is less than epsilon over 2. Then if these two are all less than half of epsilon, then their sum would be less than one entire epsilon, right? It makes sense quite a lot. So how do we do this then? Well, okay, so let's first work on this side. We'll just work from left to right. Well, for gx, what can we write this as in terms of epsilon? Okay, wait, so let's first work on fx minus a, because we know here the absolute value of fx minus a is less than epsilon. So again, we can like dissect this into more absolute value parts, and this is what we end up with. And then we know that fx minus a, that's absolute value, is less than epsilon for like there exists delta 1 such that this is true. And hence we can define this epsilon. So okay, so what I mean by it is, let's call this epsilon 1 and let's call this epsilon 2. Right? And then we have like a completely new epsilon here. Then for this epsilon 1, we want epsilon 1 times the maximum value of the absolute value of gx to be less, so we want this to be less than epsilon over 2. And to do this then, and so basically to do this, we can basically, because this is multiplication, right? We can make fractions and cancel them out. So what I mean by this is, if on this side we have q, we get some value q, and on the side we have some value p over q, then this would cancel out, and the sum, and this value here would be p, right? That's like a common logic again. And basically then we can do the same thing for epsilon over 2. So we have epsilon over 2 over some whatever thing we get, and then this same thing is the maximum value of the absolute value of gx. So then this would be epsilon 2. This would be less than epsilon over 2. And stuff like that. Okay, so what exactly is the absolute value of gx here, right? And what exactly is the absolute value of gx here, and under what conditions? Well, here we want this to be less than epsilon under the conditions of there exists delta greater than 0 if the distance between x and x naught is less than delta. So when x is closer and closer to delta. Well, when x is actually closer and closer to delta over here, we have that this is actually less than epsilon 2. So then by definition, we have, so by definition then, I'll just write this here. By definition, if we know that, so because this is true, from the triangle inequality, we know that gx minus the absolute value of b is less than epsilon 2. So gx is less than epsilon 2 plus the absolute value of b. Okay, and here the triangle inequality we're using here is the fact that the difference between two sides is always less than or equal to the third side. So if this is I and this is j, I minus j is always gonna be, so I minus j, the actual value here, is always gonna be less than the third side. And like without loss of generality, we'll just assume that this is actually greater than 0, so we can get rid of the absolute value signs. Okay, so then we know that the absolute value of gx is less than epsilon 2 plus the absolute value of b. So if this thing here is actually epsilon over 2 times epsilon 2 plus the absolute value of b, then this whole equation would be, this thing would be less than epsilon over 2. So let's do that then. Right, this would be less than, so gx is, the absolute value of gx is less than or equal to epsilon 2 plus the absolute value of b. And let's say that here, this epsilon 1 thing is actually, so let's say that epsilon 1 is actually equal to epsilon over 2 times epsilon plus like the absolute value of b. Because this condition works for all epsilon, right? Okay, wait, I forgot to, for all epsilon 1, right? So then it should also work if epsilon 1 is this value. So we have this times this, and if we cross this out, then we get epsilon over 2. And we can do the same thing here with the same tedious process, which I'll still go over because it's really confusing when, like, in the middle of a lecture, the teacher just decides to skip the other half because it's the same thing. So plus, let's again first look at this. We know that the absolute value of gx minus b is less than delta over 2. So this is less than delta over 2. This is less than delta 2. So then again, if we write this in some fraction form, for like delta over 2 times blah 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 blah, and this is like what the value of the absolute value, so this is like the value of the absolute value of a, then this would work. So what we want here is the absolute value of a times epsilon over the absolute value of a times 2, right? That would work. So then if we let epsilon 2 equals this, then we get down here, we have that. So we have this. And since this is basically epsilon over 2 plus epsilon over 2, the sum is going to be epsilon. So hence, we know that this is actually true, right? This is actually true under these conditions.